All right, y'all, you've made it. The final boss, the last lecture, lecture 8, the final lecture of Physics 7b. Bittersweet for me, might just be sweet for you. I don't know how it is. Today we're going to be talking about the kinematic equations, which are a natural extension of Newton's second law. These are 4 equations that are almost universal in physics education. You see them all over the place. This is solidly in like the mainstream commonly taught physics. That's one of the reasons I really want to make sure we hit it, is because it's one of those things that often leaving a physics class you're expected to know. So I figured we would end there. Okay, let's hop into it. Okay, introduction. What are these things? There are 4 equations that describe the motion of a point mass, so just some mass, under a constant acceleration, a constant force. So say I have some acceleration that this mass is undergoing. Now, these equations, the 4 equations I'm going to show to you in a minute, work along single components. So like, for example, say I had an acceleration that was going up and to the right. I could decompose that into its x and y components, yada, yada, yada. We only care about one component at a time when discussing the kinematic equations. So I'll just say here's a in the x direction. The component that's in the x direction for the acceleration. Okay, so what do they describe? They describe the motion of this mass. So they describe the velocity of the mass and they describe the position of the mass. So that's the main things that the kinematic equations try to get at for us, is the velocities and position as a function of time. Velocity and position as a function of time. Okay, why do we care about these things? Well, for one thing, it relates really nicely to another thing you've studied, calculus. That's just kind of like a pretty little convergence of the two fields. In terms of like practical physics, it's useful to us because we can approximate most accelerations as being nearly uniform, like nearly the same size, over short enough time intervals. So these equations describe only constant accelerations, but we can generalize them a little bit to think about non-constant accelerations too. We're not going to do that in here. Any acceleration we have is just going to be a constant straight line acceleration. So, for example, I might have an object that just accelerates uniformly at 2 meters per second squared for 15 seconds. That's an example of a block of constant acceleration. That's something we might ask you to do some math on. Also, little note, practically speaking, these kinds of equations do tend to pop up on all kinds of standardized exams, including the MCAT. So I did want to make sure that we just hit it squarely on the nose before I set you off into the world. Okay, what are we going to be talking about? We're going to be talking about these 6 kinematic variables. So these variables, these 6 kinematic variables, are the gears that go into these 4 kinematic equations, which again, I'm kind of making you hold your breath for. We'll show them in just a second. So a useful construct when talking about anything in physics, or most things in physics that we've discussed so far, is the notion of a frame, an initial and final frame. So I want you to imagine for a minute that I've got this mass, it's got some acceleration in the x direction, and let's say also it's got some initial velocity in the x direction pointing to the right. After some time, it's going to have moved to the right, and it'll have accelerated also. So it's going to have that same uniform acceleration, say. It'll have a new final velocity, and it'll have a new position. So over here it has an x initial, that's where it is right now. Over here it's at x final. So these are 5 of the 6 kinematic variables. I don't count acceleration because it's constant, so it's just the same thing twice. But the last thing is a notion of time evolution. There's some change in time between these 2 frames. So there's my 6th variable. So our 6 variables that we'll be interested in are positions, velocities, the acceleration along a given component, along, say, the x direction, and the amount of time between frames. So these are my 6 variables of interest. Okay, so all of these values can be negative except for change in time. So change in time will always be final minus initial and time goes forward. But acceleration could be negative, or left pointing in this case, velocity can be negative, left pointing. Position can be negative because usually you define position relative to some zero. So like if my position were 0 right here, I just say that's where 0 position is. Then x initial will be a negative number, x final will be a positive number. Just according to like a number line. To the left of 0, negative. To the right is positive. Okay, let's state them. Here they come. So here are the equations, the kinematic equations. There are 4 of them. And I said earlier on, they're basically just a statement about Newton's laws with a little bit of calculus thrown on top. So I've got these 4 equations. I just want to go through them and indicate what they say. So I've also, if you look on the right side of my little table here, I've shown you the missing variables. So if you're presented with a problem and you have all of your kinematic variables except for 2, there's a good chance that hints for you which equation can be useful to look at. Okay, but so let's go through them. So the first equation is a statement about position, the final position, if I know everything about the initial conditions. So if I know the initial x position plus the initial velocity in the x direction, the component of the velocity in the x direction, times the change in time, plus a half times the acceleration, which is constant throughout, times that change in time squared. So each of these 3 terms on the right contributes to my final position. So what I call this one is the initial condition fully known equation. So I know everything about my initial conditions, say, and I want to get out x final. This relates the initial conditions to the final position. Initial conditions, if I know the initial position of velocity, I can get out the final position. And I have to know the acceleration as well, right? Okay, for the second equation kind of looks daunting, but I think you will probably think of it as intuitive after I talk about it for a second here. So it tells me that the final position is the initial position plus the average of the initial and final velocities, again, like between my 2 frames, the average of those 2 velocities times the change in time. So this is an average velocity times the change in time. So basically it's a velocity times the change in time. It just happens to be an average velocity. It's the average of the initial and final velocities. Okay, that gives me my final position. So I call this the final position as the scaled average of velocities. Or I should say with using the scaled average of velocities, scaled by change in time. Okay, notice this second one, I don't have to explicitly know the acceleration. So I can just know the initial and final velocities. I don't have to explicitly know the acceleration in order to calculate where the particle's moving as a function of time. All right, the third one is basically just the definition of acceleration. That's how I think of it. So it tells me that the final velocity is the initial velocity plus acceleration in that direction times the change in time. So acceleration times change in time, recall that acceleration is approximately delta v over delta t, and it's exactly that when acceleration is constant. So this term on the right, let's draw a little arrow, this term on the right, that's just the change in velocity. So a times delta t is going to give me delta v. So this is just a statement about basically how acceleration is defined and how it relates to change in velocity. So 3 should be pretty comfortable. I'll call it the definition of, delta v even. The definition of how velocity changes under constant acceleration. Delta v under constant acceleration. Okay, and the fourth one is what I call the trickster. So the fourth one is not intuitive at all. And in the next video, I'll talk a little bit about how you get there, but I don't know that I want to spend a ton of time deriving it. So the fourth one is, it relates to squares of velocities. So it tells me about the final velocity and the initial velocity. And it tells me that that's equal to, the difference between the square of the final velocity and the initial velocity is equal to 2 times the acceleration along the given coordinate times the difference in positions, delta x. So I call this one the Trickster. If none of the other equations look useful, this is the one to check out. So notably, all of the other equations require me to know something about the change in time. So all the other ones need me to know how much time has passed between my two frames. This one doesn't. I have no need for delta t. So one notable example of when this is useful is, say that I'm interested in knowing if I take a jump off of the, say I'm like going base jumping or whatever, and I jump off of like the Grand Canyon, and I say, how much speed will I have by the time I hit, 200 meters below where I started? I don't need to know anything about the time it takes for me to fall that far. I just know how far I've fallen, and that spits out for me some knowledge about the velocity at that point, my velocity after having fallen that far. I guess in that case, that'd be the y direction, in the vertical direction. So this fourth equation is really useful when you don't know details about the time between two frames. You only know, say, initial position, final position, and initial velocity. And of course, acceleration. Okay, so again, I'm going to blow this up a little bit here just so it's even more visible. The kinematic equations are, they sometimes throw people for a loop because it's not clear which one to use. If you're just looking at a problem, what I recommend for you to do is isolate which of the kinematic variables you're missing. Which one don't you see? And that'll give you a hint as to which equation is going to be useful for you. Over time, if you just solve a bunch of these, you'll eventually get an intuitive feel for it. But since it's like only a week before the final, right? We don't have a ton of time to build up that much intuition. So that's my general recommendation. Give them a look. Look for the missing variable, which of the kinematic variables you don't have, and that should give you a hint as to which equation to explore. All right, in the next video, we're going to go through a mini derivation of these guys and maybe a few graphical examples, and then we will call it a course, I think.